Let's see. Okay, great. Well, welcome. This is the Masterclass at Connected Data World. This is entitled Graph Data Science. And this is associated also with, I'll be doing a talk on Friday, on December 3rd, called Graph Thinking, which is explores a little bit more of the business issues, but this is the hands-on practice. My name is Paco Nathan, and welcome. I've enjoyed being involved in Connected Data World in some past few editions, and really super excited about this community and what's going on right now in graph data science. We'll be working with the kglab project. So this should have been in the notes already for the master course. But there's please clone, please get clone this GitHub repo. Okay. So there's a repository in GitHub. It's for kglab. And I'll just put it out there now. We'll be working with this. So if you want to be working with the notebooks and going through examples and changing code up and trying them and all, really the best way to do this is to run it just off your laptop. And if you do get clone on this GitHub repo, and then we can talk through, there's instructions in the README, but basically do a get clone and then do a pip install on requirements.txt. So Python 3 mpip install our requirements.txt. So once you've cloned it, then just per usual with Python repos, just load up the requirements. If you want, you can use a virtual environment. It's not absolutely required, but it may be helpful. So there's instructions there if you want to use VE and V. There's also instructions if you want to load this using Conda, also in the README. Basically, you're doing a Conda install and then pip over the top of it. But there's a Conda environment that does that all automatically. So if you don't have that, please grab the repo. If you're having any troubles with it, let me know and we'll try to troubleshoot. But basically, once you've got that repo, then you can run Jupyter Lab. And I will give a brief lecture just kind of introducing what's going on here. And then, while I'm going through that, if you can just make sure that you can run this, I will also be running it. So if you just want to follow along and then go back later on and try out the coding examples, that's probably a good strategy too. This is a 2-hour course, and I'll be candid. We have about 6 hours of material here. So we're going to go through the essentials really during the 2 hours that we have. So I do think that it's recommended that if you want to, plan on working with some of this material later on after the course, that's probably wise. Also, I'll just say that if you have questions, please put them in the chat. I don't know if we can really bring anybody on stage here with live webinar, if that would really work. But certainly I'll be monitoring the chat. I'd love to get Q&A during, and we'll take some breaks where we specifically ask questions too. All right, so the next challenge is, let me see about sharing something here. Let me also drop in one more thing. There we go. So all of the slides that I'll be using, they're linked on the GitHub repository also. But there's also a online slide deck. And so this is a superset. It's actually a fairly large slide deck, but it has all the slides that will be shown here, plus others. Alrighty. So let me try to share my screen. There we go. And Chrome tab, window. There we go. Okay, great. Okay, so I'm sharing right now. This is a slide deck, and it has should have a 2D 2D URL here if you want to scan it. But the talk is all online. There's a lot of material here. Frankly, there's a lot of links to other tutorials, to different GitHub repos, to primary sources, papers, benchmarks, etc. A lot of different articles. So there's a lot of links here, and I get notes, very nice email from people maybe 3 weeks after the course, where they're like, "Hey, I finally went through the slides. I finally worked my way through all the links that were interesting. Thanks for that." So just to forewarn you, there's about 100 slides here, and it's very dense in terms of links and other background material. Hopefully that will be of some use if you find some areas here where you have questions. I'm going to be showing slides, and periodically I'll bounce back into chat just to check and see if there's any questions there. So I'll do that real quick right now. Okay, no questions yet. Okay, real brief, a little introduction about me. I made the big mistake of studying artificial intelligence in grad school, even though I was warned against it by a lot of my elders in computer science. And then I made an even bigger mistake, which people told me was just completely throwing my time away. But I decided to do a deep dive into something called neural networks. This was back in the mid-'80s, and I spent several years doing research and development in early neural networks back 80s and 90s, including becoming software lead for a hardware accelerator project for neural networks back in the late 1980s at Motorola, and then it was spun out into a company. I ended up being CTO at that company where we built hardware accelerators for neural networks, and we were actually listed on NASDAQ. It was kind of weird at the time. I mean, the only people really using it were computer vision robotics in manufacturing. But we got some pretty good customers there. But everybody just sort of looked at us like, "You're doing neural networks. Why? And why are you using hardware for this?" So it's actually kind of fun to, years later, the entire world is thinking about using neural networks for AI and hardware, like GPUs and FPGAs, accelerators. So anyway, I got a good dose of that a long time ago. And then after that, nobody cared. So there was the AI winter, and I went and did a lot of network engineering and some network security. Eventually, friends called up, and they had a new project that they wanted me to check out and give some evaluation feedback on. And I later learned the project was something to be released that was going to be called Amazon Web Services. So I got to be an early guinea pig for that, and led the first big Hadoop instance on EC2. We were a case study for Elastic MapReduce. And then from there, I became the open source community evangelist for Apache Spark in 2014, really during our hypergrowth period of Spark in 2014, 2015. So, a lot of fun in terms of machine learning and data science, leading data teams in industry. These days, I'm at Darwin, and we do a lot of work on graph machine learning and graph technologies, infrastructure, open source integration, really. We're kind of focused on large manufacturing use cases in Europe, but we're working in general in open source. And this course here, I will be talking about kglab, so let me skip to that. If you look in the slides, by the way, there's some other areas of interest that might be useful for you. I've definitely been involved in a lot of the metadata management and use of Ray and use of Rapids, so there's a lot of material there about that. We're going to focus on the open source integration part of this slide deck, so let me go ahead there. See if there's anything that I really must bring out here. Yeah, here's one part that I do want to start on. So some of the background for what we're going to cover today. There are different kinds of graphs that you'll encounter in terms of this space, in terms of the knowledge graph community. And certainly there's a large range of really interesting projects, frameworks that are available based off the W3C semantic technologies, semantic web technologies. And so RDF and OWL and SCAS and Sparkle and SHACL and all those. There's also a very large branch, if you will, in terms of labeled property graphs. And many of the commercial graph databases, of course, really focus on labeled property graphs, in particular Neo4j and iGraph and these others. Everybody using Cypher, they're property graphs. And there's a lot of distinctions between these two categories of semantic graphs or property graphs. There are some efforts to coalesce this, to basically align these two kinds of approaches into a single system of graph representation and queries. So there's RDF star and other projects that are in progress. However, I think it's kind of a false narrative. When you look at the types of graph technologies that are available, there's actually many more types of graphs, not just these two. If you listen to the vendors, there's just these two. But in the open source community, there's a lot of others. So case in point, there's a lot of work in terms of graph neural networks, which are not necessarily represented by these two bodies of standards. There's a lot of work in terms of probabilistic graphs, and we'll cover some of that. And that's really important because then you're talking about Bayesian networks and causality and probabilistic soft logic and Markov networks and a lot of applications that are super useful in industry that are not accounted for by these two standards. I want to throw the idea out there in the back of your minds that we're talking about multiple kinds of graphs. How can we align that into a common abstraction layer so that you can do work programming in Python for data science applications and just, access it as you would with, pandas, data frames, and scikit-learn and the rest. That's kind of the mission for what we're doing here as sort of a, democratizing graph data science, if you will. I'll also mention that there are some other communities. One of the things I've been doing is to help curate a list of the different graph database frameworks and the different vendors. And currently we're tracking more than 40. If you click the links here, there's a spreadsheet that tries to cover all of them and describe which kind of query language family they have and who the parent organization is, et cetera. And it's really interesting. And one of the things that really pops out when you dig into this, and again, in my work life, I've done competitive analysis for different companies. One of the things that pops out is that almost nobody does the thing where you can do Spark queries on RDF graphs and Cypher queries on labeled property graphs on the same data. You have to choose one or the other. I mean, if you go and use something like Neptune that supports both, you choose one or the other up front. And that's interesting. It's actually possible to have a graph represented that is a labeled property graph and then have a view over the top of it which exposes RDF capabilities. And so that's one thing that our team has done on behalf of commercial customers, where they can have the same data and then query it from either Sparkle or Cypher. It's possible to do it. I know we've implemented it. It's just not commercially available. And I do think that, I will share a perspective. I have friends who lead some of the graph database vendors, and we definitely have a lot of debates about this. So just to say up front that, boy, have I heard it from some of my friends about this slide. I believe in talking with customers in industry that what they really want right now is horizontal scale out for graph compute, that the big graph data science use cases in industry really are more focused on the compute than they are on the database parts of it. And this really, really, really reminds me of a time about 6 years ago when I was working with Spark, and there were a bunch of vendors that were saying, we've built a scalable SQL database on top of Hadoop, and you need to use it. You need to move all your data into our database, and then you can have compute capabilities at scale. And then Spark came along and said, yeah, actually, most of the customers don't really want another database. They just want the compute capabilities. So here's Spark, here it is. And Spark like wiped out that entire field of vendors like Greenplum and Netezza and Astra and all that. I think we're at a similar point. I think there's like 40 plus vendors saying you need to couple your database storage management of data with your scalable compute. And here's our commercial product to do that. And I think the answer in 2015 was not really. No, we don't need that. And moreover, there's a really great paper about, there's a set of papers from 2009 and 2019 from Berkeley, what was at the time, AMP Lab and now Rise Lab, where they really go in and take a look at the trends in cloud. What are the issues in physics that are driving the hardware, that are driving the choices in terms of public clouds? And then what are the economics built on top of that? So the one from 2019, here's Eric Jonas talking about trends in cloud usage during the second decade of cloud, i.e. now. And one of the biggest things that they point out is that there's been this progressive decoupling of computation and storage. These things scale independently, they're priced independently. The kinds of services that are available, whether you're on AWS or Azure or GCP or wherever, computation and storage are separate, and there are really good physics reasons and economics reasons why you want those to be decoupled. The graph database vendors, however, are saying, no, 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 keep it all in the same place. It'll be great. And I think that the industry is going to prove that to be a fallacy, frankly. And shout outs to my friends who lead companies like, Neo4j and others who are saying, well, we disagree with this. It's like, okay, well, I want to throw out this idea from open source that, respectfully, I will disagree with you. So check out that paper. Also, just in terms of types of graphs, here's a really excellent overview paper from Google recently about path query, which is a language that they run on top of their large Parquet graph infrastructure. And they, in part of it, you'll see here, table 2, part of it, this paper, they do some compare and contrast between the common types of languages for graph queries, Sparkle, Cypher, Gremlin versus path query. And if you read it carefully, you'll note Google has intentionally made some constraints and restrictions on their language so that graph queries have better properties when run on distributed infrastructure. And these kinds of restrictions, believe me, are not in Sparkle or Cypher. And as an individual, as a person who has implemented query engines for both Sparkle and Cypher, I can tell you the languages themselves have some very strange things that cause them to not perform well at scale when distributed. And what Google has done is said, okay, let's constrain the language so that we have really good properties that we can apply on very large infrastructure that's distributed. I think you'll see more tendency toward path query type languages and moving away from Cypher and Sparkle. That's my hunch of where things are headed. And there are really good reasons for that. And some of them are called Legate and Legion, but that's beyond the scope of what we can talk about today. What we will talk about today is really examples of using Sparkle. But I want to throw this out here. This is probably going to be a really important point. And I should also show just another thing, a common misnomer is, when people talk about graphs, technology and knowledge graphs, usually I hear, well, that's just Facebook or Google. And it's like, no, not really. The big verticals where graph technologies get used are finance, pharma, and manufacturing. And I can tell you that I know of a company in manufacturing that has dozens of large graph use cases, really large at scale. One of those use cases alone is larger than the entirety of Google Knowledge Graph. So what I'm trying to say is the tech giants are very noisy when it comes to we've got graph technology, but the tech giants aren't the end all be all. And in fact, in some cases, they're relatively small compared with the kind of data rates that you see in manufacturing or finance. Manufacturing, like one chemical plant will have exabytes of data exhaust. And one chemical plant will be larger than like the totality of Facebook. And there are hundreds of these, right? And I just think that when people really focus and over-index too much on what the tech giants are doing, like Facebook and whatnot, they're really missing the big picture, because a lot of the opportunities for graph data science are actually out in industry, far away from social networks and advertising. They're in use cases, like I say, finance, pharma, and manufacturing. And case in point, here's some other presentations, a lot of YouTube videos and articles and whatnot of where people running these kind of use cases have been talking more about what they're doing. One of my favorites is Stefan Reiling from Novartis, how they're using graphs for drug discovery. Also Charles Hay from Ant Financial, really, really good stuff. Stefan Lamparter and Janis Alice, respectively, from Siemens and BASF. So I just want to put it out there that I'm going to be coming from a perspective more of what's going on in industry, not so much what Facebook, Google, Amazon think. And I just want to be really upfront about that. Okay. So having said this, I will get into one little bit of theoretical discussion. When we talk about having graphs, there's a whole bunch of advanced math when you start talking about tensors and abstract algebra and all the rest. But, you know, trying to go from more practical areas of math like linear algebra into more obscure areas like graph theory, there are some bridges between this. And so we know that we can take a graph and vectorize it. We can just take some attributes out of a graph, some nodes, an edge list, representation, and create a vector. Real simple case. A lot of the libraries that you see for graph technologies rely on this. More generally, we know that we can take a graph and like take a view of it, simplify it into a matrix. And this is where a lot of graph algorithms and a lot of visualization work happens. In the more general case, a graph corresponds to a tensor, which is a multidimensional matrix. And so you can get a pretty good one-for-one between graphs and tensors. And it's really hilarious to me because when I was teaching this stuff back in 2014, whenever I mentioned graph, people get really nervous. And when they mentioned tensors, you know, by that point, they were running out of the room. And then somewhere around 2016, suddenly everybody in the industry knew all about tensors because, well, there's something called TensorFlow, so they have to know about it. But you know, the ideas have been around for a long time, and there's just this kind of mathematical transform back and forth. And most of the world, in terms of graphs, has relied on the matrix part of it, the matrix factorization. So there's something called non-negative matrix factorization, a general class of algebraic graph theory, where you can just take your graph and put it into a matrix and then do some algorithms. And for a long time, that had been what was going on. The problem is it does strip out a lot of information. And so even though this has been sort of the go-to method for graph computation for a long time, that's changing. And deep learning has changed that in a lot of ways, I would say. Sometimes you need to be able to combine what you're doing numerically with what you're doing symbolically. So graph algorithms tend to use the matrix numeric representation. Visualization libraries need that. Deep learning needs that. But when you go back out to the use case, when you have things like explainability or regulatory compliance or human in the loop, then you need to have the symbolic representation. And that's where in deep learning, for instance, yes, we crunch numbers, but then we have to interpret what does that mean in terms of the use case. So you need to go back and forth and transform from symbolic to numeric, from a rich graph representation to a very dense kind of like vector representation or tensor representation. And so I will call this thinking sparse and dense, with apologies to Daniel Kahneman. In different stages of a data science workflow, you're really working in different modes. So for instance, when you're doing data preparation and a lot of aggregations to prepare data, you're typically working with relatively sparse data. And this is where graphs come in, is because graphs are rich and relatively sparse. And that kind of processing is usually bandwidth limited, network limited. Other stages of a machine learning pipeline will be dense. So for instance, once you've put together all your feature vectors and you've got a training set and you want to train a machine learning model, then you typically shift over into a dense representation. And this is where hardware comes in, GPUs will crunch and build your deep learning model. But even within a deep learning model, you still see this. So for instance, the convolution layers in deep learning are dense and compute limited, whereas the loss function calculation in deep learning is typically sparse and bandwidth limited. So I just want to bring out that there's this idea of going back and forth between, say, a rich graph representation and something dense in a tensor or a vector. You need to go back and forth. And this is how you can really leverage the hardware and make the most out of your workflows. So there's a free mini book from Dean Wampler, and I worked with some of those machine learning software leads open source at NVIDIA. And it goes into more detail about this and more practical examples. And there is something called Legate and Legion that's coming up that I think will make some pretty big changes in this area. And I'm not going to go into a lot more detail here. But definitely check out this part. Why am I bothering to say this? And this is why, this slide here. So I mentioned before that there are many types of graphs. And if you listen to the graph vendors, they're focused on, say, doing work with Cypher, doing work with labeled property graphs. And if I were to plot that here on this diagram, this quadrant diagram, the graph database vendors are right where I'm circling my mouse. They're sort of the query languages and the things that can be done between query languages and traversals. Boom. And some of them then will produce visualizations. Boom. But they're really focused in this area. If you talk with the RDF people, the W3C people working on semantic web, they're over here more axiomatic part toward query language. They're over in that area. If you talk with the people doing graph algorithms, they are different than query languages like NetworkX and others, iGraph, a bunch of these. And they're shifted over here a little bit. But then if you talk with people who are doing network, like Markov networks or Bayesian nets or causality or something with a probabilistic graph, they're way shifted over here. But then graph neural networks are down in the bottom corner. And so what this quadrant represents is some types of graph technologies can be very robust when you're working with relatively dirty data and uncertainty and complexity. And those are the ones over on the right-hand side, boom, like graph neural networks and probabilistic graphs. Some types of technologies work really well as far as providing an analytic solution or not. So some of these have more formalism, as some have less. One of the major criticisms about neural networks, of course, is that it's not really analytic. You sort of get what you get, and then you have to try to interpret it. Whereas, with analyzing causality, you know exactly why things are resulting. And so the different graph technologies are sort of scattered across this plot. And I just want to emphasize that the graph database vendors are very, very localized, and they're not really embracing a lot of the other graph technologies. And that's what we're trying to solve here. And this idea of thinking sparse and dense is a way of understanding how to mix and match these different approaches within a workflow and come out with results and take the best of each of these different camps. And so that's why we started work on graph data science with kglab. And we have another project that is not open source yet, but we're working to get it there. There's a lot of great technologies that are available open source. They require a lot of integration work, and that's a lot of what our team has been doing because, as you may have found out, open source does not necessarily work as advertised. And trying to integrate a lot of large frameworks together is actually quite a lot of work. So what we've done is to come up with, since a year ago in October, for the last year plus, we've been working on kglab, and it provides an abstraction layer in Python to build out knowledge graphs. It's integrated with popular graph libraries. We'll talk about those. We'll be using that today. There's docs online. There's GitHub. There's Jupyter notebooks that show tutorials. There's a forum. There's the Graph Data Science forum on LinkedIn where we can discuss this and more. And the reason for this, actually, let me skip slides. The reason for this is there's a lot of great popular libraries. They just don't talk with each other. So if you're using RDFlib, how do you combine that with NetworkX? And then how do you combine that with PyVis? And how do you combine that with PSL? There just weren't good integration paths, and we got tired of having to write that code over and over, so we just created this project to do it. And then even if you do have these different camps put together, they still don't align with the popular data science technologies like the PyData stack. So a lot of our rationale was, okay, we're going to make an integration layer for these different graph technologies, but we're going to make it speak pandas, NumPy, scikit-learn, Jupyter, etc., and PyTorch. And then also under the hood, we're going to make it work efficiently with big data tools and practices like Apache Arrow and Parquet and Ray and Dask and Rapids and these kind of things that you need to have if you're going to do any kind of serious work in data engineering and cloud computing. So that's our rhyme and reason. And again, this kind of transform and inverse transform, thinking sparse and dense, being able to go back and forth between, say, a graph representation and a tensor representation, super important. And there's a lot of reasons for doing it. I mean, scikit-learn does that with label encoding. PyTorch Geometric does that in terms of their embeddings. So it's the same thing under different names, but it's a really important concept you need to grapple with. And we have a fairly aggressive integration roadmap. We've pulled in a lot of these other libraries so that you can do some combined workflows. Just kind of an overview of that. So before we start working on notebooks, let me shift over and look at questions. Okay, cool. Thank you, Mike D. Are there any other questions? Let me stop sharing for a moment and see if anybody has questions so far. Cool. Let me collapse it down. And so what we're going to do now is we're going to shift over, after questions, we're going to shift over and start running some of these notebooks, which show different parts of the tutorial, just to get some hands-on how it works. Okay, nothing just yet. Let me start up Jupyter Lab. I'll show how that works out, and then we can shift over. Oh wait, something's coming in. Meanwhile, let me start sharing again. So I'm going to share screen while that's coming up. Let me go to the proper window if I can. Yeah, it's not going to let me. Huh. Oh, there we go. Okay. Hopefully this is sharing now. I'm inside of the kglab directory where I've downloaded that. There we go. Okay, Michelle. Okay, keen to understand the use of graph data science for building knowledge graphs. For example, canonically developing graph database to build a knowledge graph. Okay, well, we'll talk through that. Great question, Michelle. Actually, really timely. That's the next notebook we're going to go into. So let's look now at how to start building a graph, leveraging this layer. And under the hood, we're using something called RDFlib. So it's the Python, very popular library in Python for building knowledge graphs in RDF. And so let me go back over. Okay, so inside of kglab, here's what you'd see at the top level. And there is a subdirectory called examples. Inside of that, there's like a dozen different Jupyter notebooks and also some temp files. But basically, this is our tutorial. And the tutorial is all online if you want to read it. It's in the online documentation. But for purposes of time, let's look through this step by step. So what I'm going to do is run Jupyter Lab. And so if you want to follow along and run this too, launch Jupyter Lab from the top level. And that should bring up, either it will give you a URL, like down here I'm going to highlight. It will give you localhost, probably port 8888, and an authentication token, which then you can copy into your browser, or it will just launch things on your browser. Mine didn't launch things automatically, so I'm going to copy in my, there. And I'm going to stop sharing because I want to share my entire screen now. Let me do that. That way you'll be able to see this part. Share screen and share entire screen. Great. Okay. Hopefully that's caught up by now. Great. Okay, so I'm inside of JupyterLab, and if you look over on the left-hand side, you should see a directory. Same thing we were showing before. And so click open the examples directory. I'm running on a Mac, and I know that JupyterLab is slightly different between, say, Mac, Windows, and Linux. Hopefully there won't be huge differences though. First thing up is data sources. So this first example 00, we have a directory, a subdirectory called dat, and inside of there are some different files we'll be using, be accessing those. So let me run through this and just show. Okay, so here's a listing of all the different data files that we have. The main thing that we're going to use today comes out of, there's a kglab data set that has metadata about the recipes on food.com, and there's approximately 250,000 recipes. And then there's metadata describing, recipe information and what ingredients it has. And so you come out with graph data in terms of the linkage between the recipes, their instructions, and the different types of ingredients. So for instance, here, if you look at one of these recipes on food.com, one of my favorites, it's called Anytime Crepes. Our family, we like to make crepes, and we have our own recipe. It involves using some beer, but kind of a French country recipe. But here's a really simple way to make crepes, and it just has 3 ingredients: egg, milk, and flour. And this happens to be food.com identifier 327593. And so you can see that over here in the metadata, you've got ID 327593, and it's an 8-minute recipe that has 3 ingredients: egg, milk, and flour. And so what we did was we grabbed a CSV file off of kglab, and if you read that into pandas and then show it in a data frame, this is just kind of taking a look at the top of it. And if you search inside the data frame, you'll find this anytime grapes. And now the trick that we do is to take 2 controlled vocabularies. And so the controlled vocabularies you can think of as a set of shared definitions. And so these are going to come out of a project called Foodon, which is actually quite an aggressive project that is building knowledge graph descriptions all the way from genomics of seeds for different types of crops, all the way through the agricultural process to grow the crops, to process the foods, all the way out to recipes, and then taking a look at, for instance, even the genomics of people who have food allergies based on different types of ingredients combined together. And it goes even further into looking at a new area of healthcare called network medicine. So there's Albert Laszlo Barabasi and his team at Foodome, where they're doing cancer research based off of what happens based on the food that you eat. Really super interesting stuff. We're going to use a couple of their components of ontology. Again, these are called controlled vocabularies. So one of these I'll take a look at in detail. This is an ontology from Foodon, which describes different types of food and different attributes of food. And so we'll be using it partly because it describes things like cook time. But it also describes things like, hey, does it have gluten? What's the glycemic index, etc. And then another ontology we'll use is about ingredients. And so here we have a controlled vocabulary that describes ingredients. And so if you want to look up milk or egg or flour, they're in here. And what I want to express is that when you're building a knowledge graph in RDF, it's really useful to go out and use these sort of standard vocabularies, controlled vocabularies. You can mix and match them. And there are thousands, and there are directories. You can go look them up. But you can think of it, if you're in manufacturing, probably any supplier that you have, say often somewhere in China, they're providing a controlled vocabulary about their parts catalog. And so you want to be able to mix and match these and then use them as a kind of overlay. Okay, and so another thing I should mention is that we have this notion of a prefix. So every item in an ontology, every item in a knowledge graph is going to have a full, complete URL, but it's kind of hard to read it when you spell it all out. So we use prefixes. So if I'm talking about what to make food ontology, I'll prefix it WTM colon. If I'm talking about a food ingredient, I'll prefix it with IND colon. Okay. And so now here, if I take a look at these ingredients, respectively, we'll call them IND chicken egg, IND cow milk, IND whole wheat flour. And so what we've done is to build up a data set based off of this. And now we'll start to work with this in the next step. Let me show that. And after I do this next step, then I'll go to questions. So I'm loaded up example 1.0. And here we'll talk about how to build an RDF graph. So just using the library standalone, not using kglab. If we import RDF, then we'll say create a graph. We'll call it G. And each graph is a set of triples. So a triple is, it has a subject, a predicate, and an object. Very much like if we're talking about, grade school grammar, the triples are composed of subject, predicate, object. There's an item in the subject, there's some kind of predicate that describes a relation, and then there's an object, sort of the value of the relation. And so here we'll create a URL for our recipe, and that will be the subject that we'll start out with. It's called S. And so what we've done is to wrap it in RDFlib. It's called a urfref, blah, blah. And we'll do this on and on throughout our work. These are called persistent identifiers. So this URL is unique. It has an identifier, which is both unique and persistent. And we can look it up somewhere. Some canonical store describes it. In fact, food.com describes this. And now we'll create a predicate. And so this is, we'll say that it's RDF type. And so if you're familiar with graphs or really any kind of object-oriented programming, there's this notion of ISA. There's this notion of inheriting from a superclass. So what we're going to say is RDF type is essentially inheriting from a superclass. We're going to say that our crepes recipe is a type of a general recipe, WTM recipe. And so we create that predicate, and now we're going to create a namespace, which is just these controlled vocabularies. How do we describe them in a dictionary? Boom. And so we'll add this WTM as a prefix binding. I just want to show you the gory details of how this is done in RDFlib first, and then we'll show you how to do it much more simply in kglab. Okay, and now I want to create an object. Remember, we're creating subject, predicate, object. So I will say my object is WTM recipe. Boom. Now I've got subject, predicate, and object. I can put them together in a triple, and I can add them to the graph. So I'll say graph, which is G, add, and then there's a tuple here of subject, predicate, and object. Boom. And now I can add more and start to build out linkage in the graph. So let's say here's a relationship called cook time. And I know that this recipe has an 8-minute cook time. I'll represent that as an object. And then I'll create a new triple, which has the same subject, that recipe, predicate, cook time, 8 minutes. Boom, now it's in the graph. And on and on, we can do this more. And so we come out with just step-by-step how to represent this. And I'm going to move ahead for sake of time, but let's go into this graph and print all of the triples. And when we do that, you can see, here we go. Here's our recipe. It has egg, it has milk, it has flour. It is a recipe, and it has cook time 8. So there's our crepe recipe. And in RDF, if we were to take and print that out, save it to a file, we call this serialization. If we were to serialize it, we'll use a format that's very popular. It's called Turtle, but it's TTL is the format. Then we can call this, and so now you can see here's all our prefixes. Recipe, it is a type recipe, and it has cook time 8, and it has these 3 ingredients. So boom, we've created a very small graph that just has this one recipe. And if we want, we can save it out to a file, and you'd see the exact same thing in the file. We can save that in Turtle format, or we can save it in another format like JSON-LD, and either case, we're going to get the same data and metadata being represented. So I just want to show you that working with W3C semantic graphs, this is what you typically have to do. And now let's try this again, but we'll use kglab. So here, open example 1.1. And so instead of going through all the gory details like I did before, instead what I'm going to say is import kglab, define my namespaces as a Python dictionary, so WTM and IND. And then I'm going to create a knowledge graph object, and I'm going to say, well, it's a recipe knowledge graph based on food.com, and here are its namespaces. Boom. And so that'll load up and create this object that we'll reuse many times. And now we'll come in and say, okay, I want to add some things to the graph. So we'll save a few steps. Instead of having to go through all the different steps of namespace lookup and whatnot, we can just do this very simply here and add the entire recipe in just a few steps. And then when we print it out, we should get the same exact thing. Great. And now there's a convenience function. If we want to save it as Turtle, we can do that. We get the same thing. If we want to save it in different ways in XML or JSON-LD, we can do that as well. Boom, boom. It's all pretty quick. But something new. In kglab, we're introducing the use of Parquet. Parquet is a column storage. If you've worked with Dask or you've worked with Spark, you've undoubtedly used Parquet very much before. There are ways of going directly from NumPy into Parquet and Arrow. So it's very popular in terms of big data. What we find is we get about 2 orders of magnitude increased performance by using Parquet in lieu of, say, XML or TTL. And so for graphs, it's really ideal. And you know, this is not going to show it. It actually, it makes Parquet look much bigger than the others, but at scale, there's some overhead you pay on the first few entries, and then after that, it gets better compression. So we'll look at this in more detail, but I just want to show, you know, we've discussed the notion of a graph and the notion of using different controlled vocabularies to describe the ontology. And then we started with a CSV file, and we were able to pull in and build a small graph to represent a recipe. And then we went in and used kglab to show how to do that whole thing over again, but in much simpler, more Pythonic kinds of ways that are integrated with pandas, that are integrated with things like Parquet. And so now you have an integration path to go out and use Dask or Spark to do some big data work. And at that point, let me stop sharing the screen and I'll cut back over and see if there's any questions. Okay, here we go. Let me scroll back through the questions. Cool. Thank you very much. Okay, Tane, doing manual research around canine cancer, relation to food and metabolic issues. Hey, great. Showed how much work this has been done connecting those data. Oh, yeah, that's really fantastic. Yeah, Tane, you know, genomics, as I mentioned, pharma is one of the really important verticals for graph use in the industry, one of the really big ones. And a lot of it is around drug discovery, and a lot of it is around genomics research on cancer. It's a really amazing area for drug targeting these days. And so I highly recommend, if you haven't seen it already, if you look at the slides where I showed, let me see, I can pick this up. If you look at the slides where I was showing some different examples of use cases, let me try to take this up. There's one by Barabasi's team, and just really super highly recommended in terms of cancer genomics with graphs like you're describing. Let me dig up a link to it directly. There we go. There's a Nature article about this work, but there's also various videos from Barabasi. So definitely check out Foodome. and Barbatsi's work. I believe it's foodhome.com. Let's see. Other questions. ICD. Okay. Okay, Michelle, how does one go about ontologies previously that do not exist? Really great question. So there are places you can look online to like look up known vocabularies. There's one called prefix.cc. There's a few of these, and they're actually mentioned in the slides. But for instance, here's one called prefix.cc, and this one just sort of shows like what's the canonical usage for certain prefixes, what are the vocabularies that go along with it. So there's a lot of these out there, and there's been years and years of work, approximately 20 years since Natasha Noy and Deborah McGinnis published their paper on ontology in 2001. So a lot of that is out there, and I definitely recommend. And the nice thing about these controlled vocabularies is they're extensible. You can take any one of these and start adding to it. In fact, I was just on a call today with chemists from a large manufacturing firm in Germany doing exactly that, taking ontochem, ontology, and then extending it for their own needs in manufacturing. And what we're talking about are hundreds of millions of nodes describing typical things you encounter in chemistry. And you know, the end result is they produce some paint that goes to BMW and they use it on cars. But to do that, they have to do a lot of ontology work. And so shout out to my colleagues in Madrid from UPM who are doing that I work with, some who may be here now, I'm not sure. But you know, you take the existing vocabularies and you extend it on for your use cases. And maybe, in fact, often you'll take two or more vocabularies and then extend them by basically integrating these vocabularies. So that's what we've done here with kglab examples, was showing how to use, you know, 3 or 4 other vocabularies, but then our own custom things. Like we know that inside of food.com, they talk a lot about making pancakes and dumplings. And so a crepe is a kind of pancake, but there's a bunch of other kind of pancakes. You know, gnocchi is a kind of dumpling, but then there are Chinese kinds of dumplings, and then there are others in Russia. So we've extended out, and you'll see some examples if you go through all the tutorial of just taking something existing and adding to it. And it's very, very much like object-oriented programming, where you take some class hierarchy from a standard library and then add your own subclasses. Pretty much one-to-one, the same thing by different names. So if you're used to working with object-oriented languages like C++ or Python or Scala, you know, all this work in Knowledge Graph, you've done it before, just under a different name. Okay, I'll jump off my soapbox. Especially when a dictionary like one does. Okay, so Nishal, maybe we can talk a little bit later. It's probably out of scope, but you're on the right path. And work to be done by inferring ontologies by combining graph and graph. Yeah. Okay. So I'm just scanning through the questions. I do need to move ahead. Yeah, inference. When I showed that diagram of the different quadrants and the different types of graph technologies like axiomatic and graph queries and traversals and graph neural networks and probabilistic graphs, the whole point there is about inference. And inference is a big word. In terms of AI, inference is, you know, a lot of the basis for what we're doing, one form of inference or another. We can think of deep learning as a kind of inference. Pretty much any supervised machine learning is, or at least the use cases are. But there are other forms of inference. And when you get into industry and you're using really large AI applications, you almost never use one form of inference. You almost always use 2 or more in sort of hybrid approaches. So for instance, you may have a large deep learning model, but then you might have some domain expertise rules. The 2 go together. And certainly if you have any kind of human in the loop, you're doing that. What we're showing is where you can do inference based off of axiomatic rules in OWL and RDFS with a knowledge graph, but then also do inference based off of deep learning, but then also do inference based off of something like SHACL, which are you know, prescriptive rules, unit tests, if you will, but then also do inference off of something like probabilistic soft logic. And when you have a machine learning workflow, how can you mix and match these different tools together for your given use case? So I just wanted to reinforce that part. I'm going to have to skip ahead just in terms of time. FTAB, we represented eggs from reference data about chicken egg. Can you expand more about how does one align variations of a concept and map it into an ontology? Yeah, that's a billion-dollar question there. You can build knowledge graphs just from raw data, and there are ways to do this. In fact, we'll show this in exercise 2 or exercise number 8, I believe. But it really helps if there's an existing ontology and you can tie into it. But maybe that existing ontology only has 80% of what you need, and then you need to extend it. So that's a big question, is like, for the thing that you're doing, is there prior art that you can leverage? And then how much do you have to extend it? I mean, this is the question that we have in open source. Can you use somebody else's work? How much do you have to integrate and add on? Maybe you need a pull request. Same thing. Maybe you need to go back to some of these libraries and say, hey, we've extended your vocabulary. We're wondering if maybe you could just include it. That certainly happened a lot. Mike D, can we represent metadata for triples in RDF, like a confidence score? Yeah, okay. So yeah, RDF is really good for representing these kind of subject predicate object. And the object may be a literal value, like it might be temperature. 8 minutes. We can represent that. But when you have to say, okay, I've got a triple, it describes a recipe, I've got some other triples hanging off, but I want to treat that whole thing as a data object and then give an attribute to the whole thing. Like, here's my crepe recipe, it was tasty. Now I can do this in a way, I can do it in a very simple case by just adding a new attribute. I like this recipe, or maybe a score. But if I want to say, I have a crepe recipe and I substituted some values and then I cooked it 5 minutes longer and I came out with a crunchy crepe. Okay, aside from just starting over and creating an entirely new object, there's no way in RDF to annotate that. No direct way. There is something that's called reification. And around the Knowledge Graph Conference, I'm sure you'll hear this a lot. It's sort of a dirty word. It's a 4-letter word that has like 12 letters in it. Reification says, well, I know that RDF doesn't support this kind of annotation, but what if we create some blank nodes and we'll just put them out there, they're placeholders, and then we can have everything else behind the blank node, and then we can annotate the blank node. And now when you go and query, if everybody could just agree that we'll assume that there's a blank node, and then you query underneath it, and oh, by the way, you may need to change your query because it might not just be a node, it might be a union of some different paths. And it gets horribly complex. And so this is one of the problems. And if you want to have a confidence score or represent uncertainty, yeah, you can do it with reification, but then suddenly all these standards that people have agreed on are pretty much thrown out the window. And so now people sort of have to agree on, well, we're going to kind of break the standard, but we're going to do it in a consistent way. If you could just kindly change your queries, that'd be great. And instead, what people find, this is why people go to labeled property graphs, is because in a labeled property graph, what you're talking about, adding a confidence score, it's trivial. It's like every node, every edge can have a bunch of different annotations, a bunch of different values. And that's also one of the reasons why we really like Parquet when we're working with graphs, is because if you want to add a confidence score to every triple, it's another column. Boom, you're done. Whereas if you try to represent this in XML, believe me, it becomes a nightmare once you have a lot of this going on. So great question. Nishal says, I'm guessing that you're talking about a very large chemical company headquartered in Ludwigshafen, Germany, and working in supply chain. And I'm interested to see what approach is being taken. Thank you. Well, I can say that you're probably very correct, although I'm not privy to give a lot of those links directly, but there are some things I can mention. Oh, okay. Thanks, Mike D. Sorry, catch up with us later. FTAB, can we choose between ontology and taxonomy? What are the guiding principles? Great question. My colleague and friend, Heather Hedden, I believe will be doing a thing here about taxonomy. I hope Heather's here. And if not, check all of her material. So ontology is a pretty big word. And when we work with ontology, there's these technologies and it's very formal. Taxonomy is not quite as formal, but it's part of it. So I can describe inheritance. I can say I have a recipe. And then I can say, well, I have a kind of recipe that's for pancakes. And then I can say, well, I have a kind of pancake that's a crepe. And then I can say, oh, great. Thanks, Marie. Marie Elaine, Heather is doing 2-part tomorrow. Highly recommended. I can do this whole class hierarchy and say I have recipe, pancake, crepe, and then under crepes, I have 150 different types of recipes for crepes. I can do that. But what if you have threads of relationships that run through all your class hierarchies, but they're not in a tree structure? Like I have something that's crepe, but it's savory and it's used as a main entree, right? So crepe Saint-Jacques coquille. I think there's a recipe like this that I really love. There's a French recipe for like seafood crepes. It's not a dessert crepe. You probably don't eat it for breakfast. I eat it for breakfast, but you probably don't eat it for breakfast. How can you take and describe recipes in a hierarchy, but then have other threads that move through them? Like, you know what? I really like to do crepes, but I only want the savory ones. Now, I can take and attribute those and have a more fine-grained kind of tree, but after a while it falls apart. Because sooner or later, you're going to run into something that has multiple definitions and different meanings. So for instance, if I use the word programming, I can tell you that if I go to a large publisher that publishes about programming, realistically, there's 8 different usages in English for the word programming. You can talk about media programming. You can talk about dynamic programming, which is an area of mathematical optimization. You can talk about functional programming, on and on and on. Programming means many things. And when you have this problem of having to represent something that means many different things, you no longer have a tree, you have a graph. And so if you go into developing graphs with this idea that everything must be my tree, it's going to fall apart pretty quickly. And so this is where taxonomy comes in. Taxonomy is about naming things. Ontology is about the whole universe. Yes, well said, team. But in practice, you're going to want to find ways to thread taxonomies through your existing ontology. And the ontology is, we had a conversation about this earlier, ontology is necessary but not sufficient. Ontology describes what can be represented in a graph, and then it sort of stops there. And so if all you have is an ontology, in industry, it's going to fall short. Because believe me, in industry, there are times where, there's an exception to the rules and you have to be able to represent that. Otherwise, your chemical factory falls apart. And that's a bad thing. So taxonomy is one of the kind of tools of being able to manage these cases and really have a much more richer representation for what you then use later on in inference. And so a super important part, oftentimes it falls through the cracks when people are talking about ontology. Heather does a really good job, Heather does a really good job talking about this. Okay, I have babbled. I want to kind of get back to some notebooks. Hopefully this is useful. Let's jump back into showing some notebooks, but I want to thank everybody. The discussions here are really great, and I hope that we can continue on later. Let me go back into sharing my screen. Thank you. Thanks, Michelle. Let me share a screen, and I'll share the whole window just to be quicker about it. Okay, so we were example 1. I'm going to go through some of these a little bit quicker because we only have an hour left and this is a 6-hour course. Here is how to take a CSV file that's actually kind of big and create a knowledge graph from it by overlaying these control vocabularies. And so here's some Python, just like we saw before. Here I've got all these different control vocabularies I'm using, a bunch of them for different reasons. But realistically, what I really want to get to is I've got this data structure that's defined that if you see the keyword water, we're going to translate that to water. If you see pepper, translate to black pepper. If you see black space pepper, translate to pepper. So this is kind of a deterministic way of having a dictionary in Python that does your translation. Realistically, deep learning works much better here. And we'll show an example of that later on. But for now, let's just say that we have like 30 of these and we want to translate them to known concepts. So boom, we'll do that. And once we've done it, Now we can come in and read our CSV file, lots of recipes, lots of messy data. And now what we'll do is carve up that into a data frame and create a graph out of it. So we'll basically be doing lookups. But one of the things I want to mention is you see a new type of control vocabulary introduced here. This is SCAWs. And SCAWs is one of the sort of the go-to methods for using taxonomy. There's other ways to do taxonomy, but SCAWs is really good. And so we'll be introducing some taxonomy here. And now we've got a graph, and let's do something else. Let's visualize it. So what we're going to do is use something called PyVis, and we're going to go in and pull this graph of recipes that we built from a CSV file and show it. And it takes a little bit, it's a few nodes, so it takes a little bit to load up on my laptop. But boom, okay, great. And so now at the center, you've got a recipe, and then you've got a whole bunch of other recipes around it and a whole bunch of ingredients around it, a bunch of attributes. And the way that this graph works, the popular things go toward the center. So the really common ingredients are going to be closest. That is to say, they have a lot of centrality, which is something you can measure with the graph algorithm. But you can guess that flour, sugar, salt, butter, these are the things that show up in recipes over and over and over again. So they're going to be central. In our case, garlic. And when I cook, garlic is right in the center. But for recipes in general, it's kind of off to the side. So anyway, half my family is from Iran and India, and we like using garlic. Anyway, let's see here. Let me show some other things. I want to show this real quick because it's super important. I'm going to analyze how long does it take to save a graph. So I've got a little bit of scaffolding there, performance analysis in Python. I'll use the time library. I'm going to say, okay, let's save this graph in turtle format. You know what? Let's save it in a few different formats. Boom. And now let's put together a data frame and show the comparison. And this is the interesting part. If you save using W3C technologies, Turtle and XML and JSON-LD, you see what the write times are, right? This takes a bit in terms of milliseconds. You get order magnitude performance increase by using Parquet. And this is just with a really small example. When you're working with hundreds of millions of nodes in a partition in a graph, you tend to see about 2 orders of magnitude performance increase with Parquet, both in terms of speed as well as size. So long story short, if you're working with big data, you want to create with big graphs, use Parquet. Great. Okay, let's discard that. Let me load up number 3. I'd shown how to do a real simple visualization. Let's go through the numbers on that. Here's a library called PyVis. It's popular. There's others like matplotlib and others. But if we wanted to build PyVis from scratch, first we have to define a PyVis network, and then we have to add each node and add each edge. And so we can do that. And so let's build up a simple PyVis graph. Boom. Real simple. But it's a lot of steps. And they aren't exactly the same kinds of nodes and edges as we have in RDF. So one of the things that kglab does is to align this. So you can automatically generate the graphs for visualization. So here, we're just going to create a knowledge graph. We're going to load the file that we created from recipes before, temp_ttl. And then we're going to define, here's our style in PyVis. And now do a projection of this graph as a tensor, and then load that tensor into PyVis. Because formally speaking, what PyVis expects is a tensor. And then boom, in a few lines of code, you've got the same graph. Actually, this is a more complex graph. But I just want to say that we're trying to make it easier to go and do some work, some Sparkle queries, some inference, some deep learning, and then boom, get graph results out just with a few lines of code. And I will highly recommend something called Graphistry. It's one of our partners at Darwin. We work with the folks from Graphistry. Really super amazing. GPU accelerated. You can do billions of nodes visualized on your laptop if you have GPUs or working in the cloud. And it's super useful in industry applications. Okay, next step. Let me check first and see if there are any questions just real quick, because our discussion is really fun. Let me see here. Unfortunately, need to drop. Okay, great. Well, hope to catch you next time, and I'll be doing a talk on Friday as well. Let me go back and share everything. Oh, and please, link up with me too on LinkedIn if you want. You can talk more on Twitter and LinkedIn, things like that. Okay, I want to show the use of queries. Queries are very important when working with graphs. Not everything is based off of queries. I want to underline that. A lot of vendors will tell you everything is a query. They're wrong. So, caveat emptor. But here, we'll show how to do a SPARQL query, which is the typical thing with an RDF graph. Let's show it in the raw first, and it's kind of complicated. So here is a fragment of RDF. We'll define that. It's got 3 people, Alice, Bob, and Dunya. And then let's just show using this in raw and RDFlib. And so okay, we loaded that, and then here's a SPARQL query. And so we'll say, we're going to look at the person, we're going to look at their surname and their email, where we know that there's a person who has a surname and they have an inbox for their email. And then we're going to order it descending by surname. Looks a lot like a SQL query, basically. Now, if I run that in RDFlib, boom, I get back a whole bunch of rows. And they're all kind of wrapped up in RDFlib. And, you can extract the information you need to, but it's a little bit hard to work with. So let's try extracting the info. You go through a few more steps. You can find out what somebody's actual last name is. Okay, a lot of backflips. Let's try this with kglab. So here we'll say, create our namespace, create our object. We've got our knowledge graph, load our file, boom, boom, boom. Okay, and now let's do a little bit more complicated query. Let's say I want to dig up recipes that we know that they're recipes. They have a definition in SCOS. We know that this recipe includes use of eggs, and then we want to find out what the time is for the recipe. And let's order these descending by time. So we're going to get back recipe, definition, description, and time. Okay, boom. And now, just for kicks, let's take the results of that query and visualize it. So here you go, 3 lines visualized. And that's the structure of the query. Not the results, but just the structure. So you can see recipe goes through. Yeah, I find this is really useful. Last time we did this tutorial, one of the participants went away and created this library for visualizing a query. Really cool, and then contributed it in a PR. All right, so now let's take a look at the results coming back in terms of a SPARQL query. And here's a data frame that describes the top 20 entries. So you see eggnog takes a day to create, or maybe 12 hours. Some types of cookies, some really great types of cookies, actually you have to let the dough rest, so they take like 6 hours or 4 hours. But most of the stuff involving eggs, they're quicker. That's kind of interesting. So we used a SPARQL query to pull some information out, a distribution of query time, recipe times out of our data. Now let's try it a little bit differently. What we're going to do here is we're going to load up another data file. It's basically the same thing we were working with before, but with some other definitions added. It's called nom.ttl. And we're going to look inside of that and see what are the recipes that have chicken, flour, and salt, like we have in crepes. Okay, and so now we're going to go through, and for every different one that has chicken, flour, and salt, we're going to start to analyze it. And we're going to say, does it also have butter? Is its title, does it have anything to do with dumpling or pasta or spaCy noodle, stuff like that? And let's just pull out a statistical distribution of that, look at a joint distribution. So, okay, here's basically the analysis by doing a query and a little bit of Python to annotate it further. And now let's visualize that. We'll take a look at that again as like a conditional probability. We'll take a look at that in a contingency table. And so we find out that, gosh, if it doesn't have butter and it doesn't say noodle, then one case is actually pretty large. If it does have butter, but it doesn't say noodle, there's a really large category. So we can actually build some conditional probabilities for that. and go back in and automatically annotate. So we could say probabilistically, you know, we think that some of these recipes can be classified either as a kind of noodle or a kind of pancake. So we'll do that, boom. And now if you take a look at this file, we've saved it, gosh, we saved it back in examples, right? Sorry. Come on. If you look at this file, it's going to be temp.ttl. And it's our recipes, but now we've extended and we've come back and we've added this kind of nom vocabulary. Pardon my humor there. We've created a new control vocabulary called nom, and in it we decide that there are some things that are noodles and some things that are pancakes. And then if you scroll down through here, you can see like our crepe recipe is annotated as a pancake, on and on. So this is a way that you can combine some post-processing in pandas and maybe scikit-learn, you know, doing some work in Python, some data science work to go back into your knowledge graph and start to add more information, more inference, and add more structure. And why do you do that? Well, in data science, when we build more and more structure into our data, then we can go and train more and more sophisticated machine learning models to do more complicated kinds of inference. So these two signals now, noodle and pancake, might be fed into a deep learning model so that we could recognize from 250,000 recipes what are some known noodles and what are some estimated inferred noodles. So I just want to show real simple techniques in data science, but you can start to get some pretty powerful outcomes. And along with that, let me show one other kind of query. There's something called SHACL. It's one of the newer additions to W3C. It's called the Shape Constraint Library. And we've integrated a library called pySHACL. And so when you're building knowledge graphs with W3C, the base standard that you use is called RDF, and that's where you represent triples. And then over the top of that, you can have this sort of object-oriented class hierarchy. You can create concepts in sort of a hierarchy of classes using something called OWL. And then you can do inference off of OWL, something called closure. We'll show that in a moment. But then over the top of that, you can go back in and describe shapes. You can describe, if you will, geometries or topologies that you expect to find within your graph. And if you find instances in the data, the graph data, that violate those shape requirements, then somebody should know. Like, for instance, if a person were applying to be a master mariner, a captain of a large container ship, there are certain types of training they have to have, because those ships can be very dangerous when they're coming into a harbor, depending on what they're carrying. And so, if you're trying to validate whether or not a person has completed all the requirements based off of the laws in a particular company for being a ship pilot, believe me, it's extremely complicated. So that kind of like regulatory compliance comes in, of saying who is authorized to be a ship captain or not. Have they completed all their training? SHACL would be one way to go into a graph and look for an individual and say, they haven't completed the following requirements. So SHACL is a way that complements OWL and RDF. And then on top of that, SCAS is a way of describing classification taxonomy. Using these four together is really powerful. I have a friend and colleague, Veronica Heimsbach, who's been doing a lot of tutorials about SHACL, and she may be here actually at the conference. Hopefully, definitely catch some of her talking about SHACL. But here we'll show a really simple example. So I'm going to create a shape description that describes a person and their name and birth and death date. If we know the death date, it has to be after the birth date. They have four types of gender: female, male, non-binary, self-described. We could go into more detail, but just for the purposes here. And they also need to have an address. And so I've got these rules here that describe, well, they need to have an address, but if they have an address, it needs to have a street address. It needs to have a postal code. So these are just some rules to describe the shapes that I expect to see. So let's load that up. And really, that shape is its own kind of little graph fragment. Okay, now here's a real simple piece of RDF data. It talks about Robert Jr. And talks about birth and death date of his biography and where he lived. Now, if we run SHACL against this, it will read the graph and then apply the rules and kick out any instances that don't fit the rules. And here, in fact, we see some violations. And so it doesn't conform. We can get a better view of this. We can print out the report text. And here in the report text, what you find is, okay, there's a literal for a birth date, but you know, it violates some of the earlier rules we had. And I believe that if you look back at Robert, his death date happens before his birth date, so that's clearly wrong. So SHACL is kicking out and saying, okay, the birth date's bad. And also it comes in and says, you know, he's got an address, but his address, if you look at it, the postal code for a US address is wrong. It's probably missing a character. It's only 4 digits instead of minimum of 5. So this is a way of sort of applying unit tests based on graph geometries, shapes. You can apply a unit test to a knowledge graph. Really important, fairly new addition, super powerful. And if you're doing anything involving like regulatory compliance with graphs, this becomes extremely useful. If you want to do this in kglab, we try to make it easier. So here we've got our food recipe, and we'll just load that up. And then we've got some SHACL constraints. We're saying, hey, a recipe needs to have at least 3 ingredients, and the definition for each recipe must be no more than 50 characters. Boom. Now let's try that and see what works. We'll run SHACL. And as it turns out, in fact, there are recipes that have descriptions that are longer than 50 characters, as one might expect. So maybe we need to change our rules. So maybe we need to change, you know, our constraints. And certainly there's, you know, other recipes that have, you know, less than 3 ingredients. If you want to visualize this, here it's a pandas data frame. And then let's take a look at doing it in PyVis. We can take all of the instances of recipe that violate our constraint rules. We've now visualized them into their own graph. So again, you can use this as like applying a kind of unit test. And so at that point, let me stop real quick because there may be questions. Okay, Roland, name of the GPU accelerated graph visualization. Yeah, cool. Graphhistory.com. Highly recommended. They have some open source versions of this. It's on GitHub. And I've seen cases of where you load up the data, you put it in front of the business unit leader, they're the expert in their domain, whether it happens to be physical chemistry or whatever, and they immediately see the patterns within that graph data by going through graph history. It's super fast. Really highly recommended. Other questions? Oh, Thomas. Yeah. Hi, Thomas. Thanks for answering that. SHACL mathematically described topology or more conceptual? Great question, team. So SHACL is a standard under W3C. So it's described in terms of, you know, if-then kinds of rules and grammars and that sort of thing. So it's effectively more conceptual. But in the area of knowledge graphs, there is something called motif mining. And motif mining has a lot to do with graph neural networks in the sense of when you take a graph and train it in a neural network, you need to, you know, focus on different areas of the graph and use those as the training instances. It's typically called embedding. And graph neural networks have some ways of representing this in terms of geometric or hyperbolic or on and on and on. But basically, you can take some little region of the graph and use that as a training vector for your network. It's a shape, and then it's a shape that can be vectorized as an input for a neural network. Now, if you think about this, say you have 1,000 different shapes within your knowledge graph, and maybe you have different attributes for some of the shapes. Like maybe here's a formula for a certain type of waterproof coating. Okay, and maybe there's 100 different versions of this. And here's a formula for a kind of shiny coating or something. I don't know. You can go back, you can turn the neural network, the deep learning model, around, right? And you can use it to like predict, like I've looked through the graph and I found some areas that seem to be known patterns. And so we typically call this motif mining. And so in knowledge graphs, we'll talk about identifying motifs within a graph. These are shapes. And so it is possible to construct SHACL constraints from motifs that have been mined out of a graph. So you can cross from doing deep learning into motif mining, and then from there into SHACL representation. Probably take it as more of an agile, iterative approach where there's some human in the loop involved. There are ways to semi-automate it, but then you probably want to be reviewing it. One of the people working in this area, a friend of mine, I really love his work. He's also a really prolific author. His name is Maciej Besta. He's at UTF Zurich. And let me dig up his paper on motif mining, just as an example. But this is where we're starting to see some mathematical formalisms that bridge between this notion of, hey, I've got a big graph. Hey, there's a bunch of shapes that are interesting in there. Hey, I can use deep learning to find where those shapes are. Hey, I can translate those into SHACL constraints. Hey, now I can iterate on my graph and do some data quality checks. Cool. So, this is what we're starting to see are practices like this emerging for, more mathematical formalisms, leveraging topology, leveraging geometry. And I'll say, allegedly as a mathematician, when you mention the word topology, most of the mathematicians in the room will scream, running in the opposite direction. They love to hear the word geometry. It's a lot easier to work with. Topology is a lot harder. In graphs, you really are working with topology. So you're going to see this in the community. You're going to see people talking about geometric deep learning. If somebody says topological deep learning, a lot of people will go, no. Topology is a lot harder, but it's more valuable. There are ways of doing very formal topological analysis. You see this in terms of triangle counts and then different representations of triangle orientation, where you can build up larger structures based off of more complex topology. I'm super interested in this area, and I've been doing some work in it. And there is an area in data science of topological data analysis, TDA, and something, if you're into math, there's something called persistent homology. There are ways in linear algebra to represent topology. They're very complex. But there are tools of being able to go into graphs and find the shapes and segment them. One of these is called Data Refiner, and it came out of Google's graph effort to understand marketing segmentation, really large graphs that they use in Google for advertising, where they can segment the graph and then target different campaigns on different segments. So topology is becoming more and more of a thing with graphs. If you're going to do this kind of work, you probably want some GPUs somewhere nearby because it's very expensive. But the blending between these areas of mathematics is super interesting. A lot of commercial value. Most of the time when we've tried to do it in industry, everybody said, hey, it's too complicated to think about and we don't have the hardware. Well, guess what? With these open source technologies now, it's no longer too complicated to think about. Also, with GPUs and FPGAs, we have the hardware. So sky's the limit. When do we run SHACL validation on the graph? After ingestion. Probably after ingestion, because you really need the graph to operate on. So you can think of having sort of a scratch space of a graph and then applying some SHACL rules to it. So think of an iterative approach to building a graph that way. Maybe bring in one data set, check it, bring in another data set, check those. And this is kind of more of a formal approach to, if you will hear people like Airbyte talking about EL, not ETL, but let's do extract and load, and then do our transformations after we've loaded. So one of the concepts that's very current in data engineering is let's just defer the transformation parts of ETL until later, and then we can bring everything together in one place, analyze it, iterate on it, and then formalize our transformations in something that are basically, GitHub actions, right? They're CI pipelines. I could talk more about that, but that is one of the really big use cases in industry for graphs, is managing much more complex kinds of data integration workflows. Bharat, can you SHACL to test whether relationships are two-way, broader than two-way? It's a good question. The kind of graphs that we're talking about right now are directed. So when we're talking about RDF, it's a directed graph. So, there's no such thing as a two-way relationship. You would have to have some type of axiomatic description of a relationship having an inverse transform. And in fact, that exists. We use RDFS for that. So you can come in and say, this relationship goes both directions. But what that means is you'll populate your graph, and then you'll have to run an algorithm that does closure, that does inference on OWL and RDFS, and it goes back in and it says any place where there's a bidirectional possibility and it doesn't exist, just create another triple. So you end up taking a graph and then adding a lot more to it to be able to get inheritance that you would sort of get for free if you were doing, Scala or Java or Python inheritance. But that's how you represent 2D or two-directional. That said, a lot of the graph algorithms, and unfortunately, one of the popular graph query languages expect two-direction links, that they're bidirectional or non-directional graphs. And so sometimes you have to take your graph data and drop it into a matrix and say, oh, hey, magically, this directed graph is suddenly not directed anymore. Do what you like. And there are reasons for that. Mathematically, we can put some boundaries around it and say, yeah, okay, this is kind of okay to do in a special case. Unfortunately, one of the most popular graph query languages, which I shan't mention, Cypher, allows for just completely forgetting about directionality and actually doing some really strange things with directionality are actually possible in the language. And as it turns out, when you try to compute that at scale distributed, a lot of your computation falls apart. So yeah, the bidirectional part is an interesting thing to manage. And you really need to understand that in terms of the graph representation, but also the queries and algorithms. Let me go down. What about checking constraints as part of the commit, which added the data? Yeah, sort of. I think this is really, I know we're spending time on this, but I would say check out Airbyte, and I'm going to pull up, let me pull up something, the data exchange and Airbyte. There's a really great interview that one of my colleagues did. Ben Lorica, if you know him, he runs Gradient Flow, and he has a podcast called Data Exchange. A lot of great machine learning and data engineering there. I will put in a conversation that he had about some contemporary themes in data integration. So I think you want to think about data integration as a continuous integration problem. And there's some really great tooling for this now. We've just started on infra at IKEA. Oh yeah, hey, great. Tane, maybe we can talk offline because I'm working a lot with industry people, and part of the reason for having this conference in this community is to network with amongst there's a lot of good people around here. I also have another friend working at IKEA in a related space, so we may have some common ground there, but I'd love to talk more. Brad, when I was importing data to RDF with Pool Party, it expected two-way relationships to be valid. Yeah. So some of the graph database vendors, like I say, it gets a bit murky, and some people kind of blur the lines. Again, if you're working in RDF, formally speaking, mathematically speaking, in terms of AI and inference and all the lovely things that we do with math, that is, supposed to be, the directionality of the graph is supposed to be well defined. Some of the graph database vendors are like, yeah, let's just see what happens. How about we just relax that constraint and see what happens? What happens is if you have a billion node graph and you have bidirectionality in places where it shouldn't be, then you can introduce cycles that shouldn't be, and then you'll find that your graph algorithms no longer compute. So it gets really interesting when you're working with data quality issues at scale. And again, if your data integration pipelines aren't really tied down and don't have a lot of quality checks, you can end up with problems that might take your team a week or two to troubleshoot just because some cycles were introduced that weren't supposed to be there. And believe me, I've seen it. And super smart people on teams are just pulling their hair out trying to troubleshoot the data for like weeks before they can get back to production. So that's why I'm making a big point about directionality, is that it really can be, especially in machine learning, it can be a really big risk if it's not managed carefully, because you can start making inferences about things that just literally don't exist. Okay, cool. Let me jump back into great discussions here. I really appreciate that. Let me jump into showing some more notebooks. Yeah, okay, X5. X6. What is, cool. So here's a general category of something called graph algorithms. And one of the real reasons why we started writing kglab was because we kept having to do work in, say, RDF and some work in SPARQL, but then we wanted to run graph algorithms. And the two just aren't connected at all. And in fact, they use different kinds of graphs. So what we did was to come up with this abstraction layer to blend these two. And then once we did that, we're like, well, if we can do that with NetworkX, why don't we pull in PyVis? Hey, why don't we pull in? And then we ended up, 20 libraries later, we have an abstraction layer. So let me show, here's our knowledge graph, our food recipe knowledge graph that we've done before. And here's a SPARQL query. And we're just going to take a look at recipes, and we're going to say which recipes link to which ingredients, basically. So I'm going to create a very simplified graph just of recipes and ingredients by using this kind of subgraph projection as a matrix. So I'll come up with an adjacency matrix. And if you've done work on recommender systems before, you've probably encountered this term. If you've ever studied things like PageRank, you've almost certainly heard this term, bipartite. So I can have a data structure where I have links between two sets, but each element in each of those sets, they don't link within the set that they belong to. They link to the other set. They don't link amongst themselves. And so that's something that's known in graph theory as a bipartite graph. Once you have a bipartite graph, you can do really interesting things with large sparse matrices, like calculate page rank orders of magnitude faster by doing power method. So what we're going to say is we've got a bipartite graph. There is no instance in our recipes where eggs links directly to flour. They always link through a recipe. And so what I'm doing is to say, great, I'm going to drop my simplified recipe graph into a matrix, adjacency matrix. Then I'm going to build up a NetworkX graph from it. And I'm going to say, oh, by the way, this is a directed graph, like we just mentioned. And it's also, we know it's bipartite. And once we know that, then we've got some strong guarantees on the kind of math that can be applied. So first thing I'm going to do is start to take a measure. Here's a graph algorithm that looks at the density, which is the ratio of edges in the graph to the maximum possible of edges it could have. So how populated is it? 1 is an upper bounds. We've got a fairly sparse graph here. It's 0.016, etc. That's a really interesting thing, especially from a data engineering perspective of like, what kind of resources am I going to need based on the type of queries I'm running? Okay, so density is something you probably want to measure. Here's another instance of running NetworkX. Let's do a breadth first search. And let's start with butter as an ingredient and then see what else we can reach. Okay, 0. There aren't any edges returned because butter doesn't have any neighbors. It's a directed graph. And so you've got recipes that link to ingredients. You don't have ingredients that link to other ingredients, right? So let's relax that. And now we get to this point, let's take our graph and convert it from directed to undirected. And now let's do a breadth first search going 2 hops out. Boom. And now you find that butter is 2 hops out, linked with flour and milk and blah, blah, blah. And you can see how these are represented. You can do some ranking on it. But this is where there may be times when you need to relax that constraint. Then you can do interesting types of analysis. Okay, now let's go through and take a look at, here's recipes and ingredients. We can specify a bipartite relationship, separate the graph, if you will. And here's actually an instance of using topological analysis. It's something called a triadic census. And so there's a great paper about this, and there's some libraries that have been integrated. But basically, different triangles, different triads have different canonical shapes, if you will, and there's an encoding for that in terms of triadic census. And so here we can decompose our graph into a census and start to measure how many occurrences of different types of shapes are there. Of course, if you wanted, you could go beyond triads and you could have more complex shapes and start to take census of them and then have a statistical measure of, gosh, what are the motifs that occur within my graph? A lot of good uses for that, but I just want to show a simple case. Another category of graph algorithms has to do with ranking. And so here we'll do centrality. We'll measure degree centrality, one variant of centrality. And this is kind of like the graphic that we showed before, but basically what is connected to other stuff? Where is Kevin Bacon? So here, as it turns out, the most connected thing happens to be flour, as you might expect. Eggs, salt, butter, the most popular ingredients are going to be the most strongly connected. And let's plot that. Boom. And so now we can get a small graph of the really densely connected things, the highest ranking connections. And if you dig into this, you'll find out what they are. But it's what we just said, butter, flour, etc., and then the recipes they link to. Now, there's something called k-cores, which is kind of like peeling an onion. Let's say we have this representation of how things are densely or sparsely connected. Let's start peeling off the different core connections. So we call these k-cores, and let's just peel them off one by one. Boom. Okay, and so what this allows us to do is take a really dense representation, a strongly connected graph, and start peeling off the major parts of it. What are the major shapes that we're finding in there? And take those off one by one. It's kind of like principal component analysis if you've done PCA for any sort. And frankly, this is a clustering algorithm. There's almost a one-to-one correspondence between this and things like k-means clustering. So it's a kind of graph clustering, if you will. Here, now let's take this a little bit further on. Let's do a sorting based on these different cores and see how they rank. And okay, so this is a way of approximating a centrality measure. Mathematically, they're very, very similar kinds of rankings. And yeah, they come out flour top, egg, salt, etc. Now, one of the special cases of this is something called PageRank. And so PageRank, formally speaking, is a stochastic variant of eigenvalue centrality, if I've got that right. So let's do PageRank on this. And as it turns out, the PageRank on this graph shows that the flour is most densely connected, eggs are next, etc. This is really good, and you can get into this certainly in like supply chain kinds of analysis where I've got a bunch of vendors, I've got different parts, different supplies, and they're going into some of our production operations, and then we can see where they're going out to customers. If you start to run centrality analysis or k-core analysis on that supply chain, now you can find out like what are the most critical supply components, and really where is there overlap in vendors, and just these kind of rankings. You can start to tease the graph apart into the really, really interesting components. So again, logistics and supply chain, this is super important. You can see similar kinds of cases in finance for like value chain calculations in terms of corporate finance. I barely scratching the surface. We have integrations with NetworkX and iGraph, a lot of really great algorithms there. I was showing NetworkX. Let's take a look at iGraph. Here's where we used Leiden. And so we can literally do a very popular form of graph clustering. So I'll take the famous Zachary Karate Club example. And I'll run a Leiden partition on it. And then within this club, I'm partitioning it into 4 different subgraphs. So you can see that there. Now I can turn around and let's do this more simply in kglab. I do a SPARQL query, build up my submatrix, and then I will build up, let's partition it based on things like, is it based on batter? Is it a pancake? Is it a noodle? And community detection. Okay, now let's visualize that. So I can take my recipe database and start to visualize partitioning based off of, do we think that this is a kind of pancake? Is it a kind of noodle? Does it require a batter? Does it require a dough? Starting to apply some machine learning and some categorization here. And of course, then these signals which cluster you belong to can feed into feature engineering for doing some deep learning models and stuff downstream. Okay, that's a lot of material. We have only a little bit more time, but let's shift back and see if there's any questions. Okay, great. One of the first talks you've seen where I find the graph. Oh, cool. Okay. Yeah. Thank you, Tane. I hope you're pronouncing your name right. I'll find out later. Yeah, that's a really great example of like Borges' Library of Babel. And in fact, yeah, I love that reference. I used that reference one time in an article. Borges really defined the notion of artificial intelligence and what we're doing with graphs. The other person who did that a long time ago also, Charles Sanders Peirce, one of the most prolific 19th century scientists, founder of the US Geological Survey and others. He came out with a notion of something called semiotic graphs, basically knowledge graphs, in 1886. But yeah, Borges' example is just perfect. Okay, no further questions just yet. Let me jump back into a couple other examples. We've got 10 minutes left. So let's see. I'm sharing the screen. And let me go back to there. Okay, let me knock these out. And 7. Okay, I've talked before about inference. And so here I've got sort of a constructed example. I've got this data set called gorm.ttl, and it's a small community of Vikings. And if you look at details, there's a bunch of people who live in this village. There's life and Bodil, and there's things they like to do, like fighting and berserking and stuff like that. So we've got this really small graph that describes a Viking village. And now we're going to go in and we're going to do a couple things. We're going to measure the nodes and edges, get some basic stats about them. Okay, so this is a graph. It's pretty small. It's got 15 nodes and 25 edges. We're going to look at some relationships here, ancestor of, and it comes out empty. So we defined our graph, and let me see if I can dig up Gorm, show you an example of what Gorm looks like real quick. Here we go. So we define this, and there really are some bidirectional relationships here, because we describe that, say, Bjorn is a child of Gorm. We don't describe that Gorm is an ancestor of Bjorn, but we do have an inverse relationship here in terms of it could be inferred. So when we first run our query without doing that inference and look at who are the ancestors, it comes out empty, which is not what we want. Also, who is the spouse of whom? And we don't really get much. We just get Bodil and life are married, but we don't get that bidirectional relationship. So, and the other thing is like, okay, they're Vikings. Who wants to fight? Nobody. Okay, well, clearly there's some data quality problems because we got a Viking village. Somebody's got to fight, right? And there's somebody who's an ancestor of somebody else. So let's do this. We'll use something called closure, which is to say we're going to apply all of the axioms that we know about in our owl ontology and make sure that if something is represented as a unidirectional relationship, that we have its inverse relationship as well to make it bidirectional. But we have to do that explicitly. So we just call this in one line, owl closure. And now when we print it out, you'll find out that there's spouses and that there are marriage relationships. You'll also find out that now we've gone from 25 edges to 156 and from 15 nodes to 75. So approximately 5x. We've increased the size because we've added all this additional information by doing inference and closure. And now when we query it, who's an ancestor of whom? Bingo, we've got it. And now who's married to whom, or who are spouses of whom? We've got that described. And now the big question, of course, first off, let's just take a look. We'll measure predicates and objects. Great, we have some good measures on that. Get some tallies, some different measures you can use statistically. But the big question is, they're Vikings. Who wants to fight? So we're going to use SCAs, and we're going to use taxonomy to infer in a more broad or narrow kind of category. And so we're going to say that, well, yeah, fighting is important for Vikings, but there are different types of fighting. And if you don't explain the taxonomy of those relationships, your queries are just going to miss it. So what we're going to say is there's two types of fighting. There's pillaging, there's also berserking. And once we add these relationships in and run inference with SCAs, then we go back and say, okay, the Vikings, who wants to fight? Now we know that Bjorn wants to fight and Gorm wants to fight. Much more Viking-like. So apologies for the constructed example, but this illustrates how to leverage a form of inference and how to start out with a fairly compact and terse representation of your knowledge graph, but then apply inference and enrich the graph fivefold, and then get a lot more critical information out of your queries. In the interest of time, I'm going to move forward and then take some examples at the very end. So in the interest of time, let me show this. This is a really interesting area that most people just haven't even heard of. It's called statistical relational learning. You may have heard this in terms of causality analysis, or if you've done sophisticated work with, say, probabilistic models like Bayesian inference, you've probably run across this too. We're going to use a library called PSL, probabilistic soft logic. And I'm just going to run through this real quick. I'm going to visualize a very small, this is a professor, Lee Skatur, who leads a lot of this research, and these are her grad students and where they live and what they're interested in. Okay, so I'm going to create a model just real quick, and then I'll talk about it. But basically, within this small community, we have some relationships. We have who's neighbor to whom, who likes whom, who knows whom. Some of these relationships we know explicitly, and we can add them explicitly. Some of them have to be inferred. So now what we're going to do is we're going to create some rules. We're going to say if two people have lived in the same place and they're both graduate students of the same professor, they probably know each other, right? And if they don't live in the same place, they're less likely to know each other. If two people have a common interest and they're both in the same community, they probably know each other. If they know a third person, then you can create a triangle around all three. And otherwise, they probably don't know each other. So these are 5 probabilistic rules. And we'll define these. They have some different weights, but pretty straightforward. Now we apply mathematical commutativity rule that if a person 1 knows person 2, then vice versa. So commutativity, we create this bidirectional aspect. And now we're going to run this probabilistic model. Boom. And what we've done is to run these rules and look at the different people and assign uncertainty values, if you will, or confidence values, if you will. And we've created a subgraph. We will query that. Let's just take a look at who lives near whom. And then, okay. And so if I look at the raw data, I'm going to end up with a data frame. It's kind of hard to read. But if I put it into a pandas data frame, now you can get this kind of trace of just like who likes whom, observed data. And so we've got a list of that. Here's person 1, person 2, and this is kind of ground truth for who we know who likes whom. But now we're going to start to load up some more data, both ground truth as well as some targets, some known unknowns, if you will. And okay, and add up some more. I'm just running through this real quick. And now finally, we've built this thing. We've got our graph. We've got 5 rules that are in there. We've got targets for the sort of known unknowns we want to measure. And now we do inference. And so this will take a few minutes. But we're running through and doing a probabilistic inference across this graph of do these rules apply or not? And if they do, what's the confidence for a given node that it has a certain relation? And so, boom, it's complete. And now if we come through, we'll pull, take a look at results and just take a look at a data frame. So now we've got a truth value, the truthiness for each of these predicates for each of these nodes. And you can see some of these are basically 1, and some of these are basically 0. Some are in the middle. They're kind of unknown still. Let's take a look at that in more detail. So I just real quick, I'm going to create a data frame with its truthiness and the difference between the inferred truth versus the ground truth. What's the difference? And if we draw a histogram of that, basically there's a whole bunch in the middle. The ground truth matches the inferred, the predicted certainty. But there's a few edge cases on either side. Somebody should check those because either the rules are wrong or the data is wrong. But what this allows us to do now is come back and and probabilistically add attributes to our graph. So we can basically train a predictive model for where we think people probably know each other versus where they probably don't know each other. And on top of that, now each one of these nodes, each one of these relations has a confidence value. They have an uncertainty value. This gets really interesting. It's much overlooked. I think there's a lot of industry use cases. I have 1 minute left, so let me show one last thing. Sorry for the time. This is a deep learning example. We're going to take a whole bunch of different types of ingredients that we know about, and then we're going to analyze all of our recipes and build a deep learning model. Boom, boom, boom. I'm going to do this real quick because we only have a little bit of time. And then what we're going to do is go back and resample from the deep learning model and see whether or not we believe the predicted labels. And the way that we do that is, okay, let's just focus on one of them. Let's say basil. So we take a look at all of the things that are close to dried basil. And it turns out if it says dried basil leaves, it's really close to being dried basil. If it says dry basil, same thing as dried basil, on and on. But then you get into the tail of the graph, which is much different. And there you might have a recipe that involves dried basil. So what I want to express is, let me just go through here. Boom. We can plot out the results from the deep learning model and say that the stuff in the top, we can disambiguate, we can deduplicate because these things are synonyms. This stuff down here, they're not synonyms, they're related. It might be basil and oregano or marjoram. But the stuff out here, it's not even an herb. It's a recipe that uses the herb. So you can build a deep learning model that can segment the data similarity and start to attribute, do we have a deduplication problem or are we actually seeing a usage? And so here we've built out a little model for that to show it. We can go into much more detail. This is a way that you can construct knowledge graphs from raw data. And I don't have a lot of time to go into that in a lot of detail, probably outside the scope of this, but I did want to show you these kind of things are possible. Questions. Lots of computation you do is happening in Python. Yeah, okay, so there's a lot that's going on in Python, different stages of data. Yeah, good point, Peter. So remember, I started out by, in a lecture, showing this notion of thinking sparse and dense. And there are times when you're doing computation in Python, which are very sparse. Like I start out with a CSV file and I want to convert CSV into a controlled vocabulary. I might use a machine learning model to do that, but the data is pretty sparse. But then there are times when I go and calculate a deep learning model, right? Train it. That's very dense. And it would be much better if instead of doing that just in Python, I was doing that on a GPU, like using QDF and PyTorch and using GPUs. So that's the dense part of it. And so that's where you want to be staging the data and really thinking about, okay, how am I going to try to optimize and accelerate different portions of this? That's what I was trying to say. And it really helps when you build up progressively into larger and larger graphs that you're doing this in a reliable way, and really leveraging the hardware where you can, because otherwise you're going to get into a billion node graph that a friend of mine had this problem where the vendor sent a new release of their graph database and they had a 5 million node graph. And the thing that took 2.5 days to load after the release took 26 days to load. And that was just the loading time for the graph, let alone the queries. So use your hardware wisely. What are the most commonly used or highly adapted OWL reasoners within the industry? Yeah, that's a great question. There's been a lot of work in W3C ever since 1998 on being able to describe, what you want to do with reasoning. The trouble is those are usually fairly static rule-based approaches. And, at the same time, the machine learning community was saying, well, what if we just approach this in an empirical way? And, now we have deep learning, now we have reinforcement learning, and now we have self-supervised learning. So it's kind of been parallel tracks of can we do this in a very discrete way with a bunch of rules and have reasoners, or can we just dump the data into a model and train the model and use deep learning or use machine learning? And I'll preface this by saying that my graduate advisor was early in machine learning and actually got denied tenure at Stanford because the powers that be were like, we need to focus on reasoners. These people doing machine learning, they're just playing around. They're not, they're not really academic. So Stanford actually denied tenure because somebody was working in machine learning. That was in 1985. Things have changed since. I just want to say that there's a lot of contention between different approaches of inference, but there's a lot of good reasons to do al-reasoners and do some type of inference based off of that kind of reasoning. I tried to show that with the Viking example in a really trivial case. There's even more reasons for using the best of both and applying the sort of rule-based reasoning along with results of machine learning. And that's part of what I was trying to show in this last example of how to infer the usage of an herb in a recipe. Because, deep learning is great. It's kind of hard to explain how it's arriving at a decision. But if you mix and match with rule-based systems and machine learning, then you can get to better explainability. And this is what we're seeing as hybrid AI systems. As far as the types of al-reasoners out there, there's a lot. And I'm probably not the best person, although there'll be some other folks who would be really good in this particular area at the conference. Peter is a good person to talk to about this. Thank you, Peter. I should read ahead in the comment thread before I start off. Okay, can you define probabilistic rules using ontology and inferred in triples? Yeah, so can we take what we've learned out of our graph and then start to construct rules? Yeah, and short answer, some of the active research area, but some of the work in motif mining is effectively starting to do that. So again, crossing that bridge from I've got a graph and I can define some shapes in the graph and I can build models to identify those shapes. And then I can reflect out of that. I can represent those shapes in a formal way using SHACL or some sort of topological analysis. Can we basically connect the dots and create a full circle on that? And yes, and great. Probabilistic rules require numeric reasoning. This is beyond most of the reasoners. Yeah, great. So good point, Peter. There are some areas of RDF engines that will allow more of that kind of numerical reasoning. I work in an area where we can query both RDF and Sparkle, OWL, that kind of stuff up at one layer, but then Cypher down below and possibly some other kinds of query languages. So we can do reasoning that's both numeric and symbolic. We've done that. Hopefully, a very large chemical manufacturer is reviewing now how to push that open source. Thank you, Lee. Thank you, Ebru. Great to see you. Sebastian, I know we're up on time. Thank you, Peter. I'm glad you could join us. I'm around. I'll be at the conference. I wish you all the very best. Please link up. Thank you. Good point. If you want to get a hold of me, I will end by just showing this one slide here. And somewhere at the end. Yeah, great. So you want to get a hold of me, I'm at DerwinAI/Paco, Pacoid on Twitter, I'm on LinkedIn. Definitely catch up. A lot of great forums, and look forward to the rest of the conference. And I wish you all the best. Thank you very much.